There is a metal cylinder sitting on the surface of Mars right now. Inside it is a core of rock, roughly the size of a piece of chalk, drilled from a stone that the science team gave the informal name Cheval Falls during the summer of 2024. The rock contains markings, small, dark, distributed through the material in specific patterns. The researchers who first examined them described what they saw using casual language that carried an enormous amount of weight. Poppy seeds, they said. Leopard spots. On any rock outcropping here on Earth, formations like those would appear in the reference section of an astrobiology textbook as unambiguous indicators of microbial biological activity, the kind of thing a graduate student would recognize on sight. After approximately 1 full year of careful internal review and external peer evaluation, the most rigorous scientific vetting process available to researchers working on material this consequential, NASA officially reclassified that sample last September. The agency's position, stated formally in a peer-reviewed publication, is that the sample contains what they call a potential biosignature. The word potential is doing an enormous amount of work in that sentence, and the people who chose it knew exactly what they were doing when they wrote it. No scientist involved is willing to say the word life. Not publicly. Not yet. The language is calibrated, careful, and precise, in exactly the way that language has to be when what you might be describing is the most important discovery in the history of the human species. But the cylinder is still there. It has not moved. It is resting on the surface of a world that by best available scientific estimates ceased being hospitable to biology of any kind roughly 3.5 billion years ago, give or take a few 100 million years. The wind blows over it. The sun rises and sets over it in the thin, cold Martian atmosphere. No one is watching it. No instrument currently on Mars is capable of analyzing it with the precision needed to say anything definitive about what it contains. The earliest that cylinder realistically comes home to Earth is somewhere in the late 2030s. That estimate is itself uncertain and has been slipping. Tonight, we are going to talk about that rock. But this conversation is going to extend far beyond that rock, because Mars is only the most conveniently visible dead world in our neighborhood. It may not even be an unusual one when you zoom out to the scale of the galaxy. What this entire conversation is actually about is a question that rarely gets asked directly in this particular form. Partly because following the question wherever it leads takes you somewhere genuinely uncomfortable. Somewhere that changes how you look at the night sky and the planet you are standing on, and what it means that you happen to exist right now in this particular moment. The universe, as far as current instruments can confirm, contains just over 6,000 worlds orbiting other stars. Credible scientific estimates suggest hundreds of billions more exist within our galaxy alone, most of which we will never directly detect. The instinctive human assumption, when confronted with numbers that large, is that some meaningful fraction of those worlds must host life, that someone, somewhere out there across all that space, should be home, that the sheer scale of the thing makes life almost inevitable somewhere other than here. But the closer scientists look at what it actually requires to keep a planet habitable long enough for life, not just to start but to persist and develop into anything recognizable, the more the real story starts to diverge from that intuition. The story may not primarily be about how often life begins. It may be about how rarely it continues, about how many windows open and then close before anything meaningful passes through them, about how many worlds got their shot and lost it before anything on those worlds was equipped to understand what was happening. By the end of this, the night sky is going to look different to you. Not empty, the opposite of empty. full of something quieter and older and more final than most people imagine when they look up, full of something that already happened, something that finished, something that, in many cases, ended before the earth itself had fully solidified. Here is where most people's mental model of the universe goes wrong. When the question of whether anyone else is out there comes up, people tend to organize their intuitions around two possible answers. The first, the cosmos is teeming with civilizations, and we simply have not managed to cross paths yet, or we have not been listening carefully enough, or the distances are just too large for contact to have happened. The second, the cosmos is empty. We are the single, improbable exception in an otherwise lifeless universe, and everything we see out there is rocks and gas and radiation and nothing more. Those are the two poles. That is the binary that most public discussion of the Fermi paradox operates within. There is a third option. It is the one we are walking toward tonight, and it is the possibility that the universe is neither of those things. It is the possibility that the universe is full, genuinely, ostensibly, historically full of worlds where the conditions for life assembled, persisted for some span of geological time, and then dissolved. Worlds where life may have appeared, run its course in whatever form it took, and then stopped. Worlds where the chemistry was right, the water was present, the energy was available, and something may have used all of that, and then the window closed, and whatever had been using it either ended or never fully developed in the first place. Worlds with porch lights still burning in the sense that their stars still shine on them, but where the houses they illuminate have been dark for longer than complex life has existed on this planet. The number to begin with is 6087. That is the confirmed count of planets outside our solar system as of January 2026. According to the NASA Exoplanet Archive, the official registry where verified planetary discoveries are formally logged after passing the community's standards of evidence, NASA crossed the 6,000 planet threshold in September of 2025, which was itself treated as a milestone worth acknowledging. To put that figure in some kind of human scale, there are approximately 195 recognized sovereign nations on Earth. We have confirmed more worlds orbiting other stars than there are countries on this planet, by a factor of roughly 30, and those are only the worlds we have actually managed to detect with the instruments currently available to us. The estimated true number is orders of magnitude larger. The Milky Way contains somewhere in the neighborhood of 200 billion stars. Data accumulated from the Kepler Space Telescope and its successor, TESS, both of which were specifically designed to find planets around other stars by watching for the tiny regular dimming that occurs when a planet crosses in front of its host star. From our Isaacs perspective, suggests that essentially every star in the galaxy hosts at least one planet. Many host several. Some host systems with more planets than our own solar system. When astronomers take those per-star averages and multiply them across the 200 billion stars in our galaxy, the result is a figure somewhere in the hundreds of billions of planets in the Milky Way alone. That estimate does not include the hundreds of billions of other galaxies in the observable universe. Of those hundreds of billions of planets in our galaxy, the most current estimates, derived from the statistical properties of known exoplanet populations, place the number sitting within the so-called habitable zone of their host star at somewhere in the tens of billions. The habitable zone, as a concept, refers to the range of orbital distances from a star at which liquid water could theoretically exist on a planetary surface, given certain baseline assumptions about atmospheric composition and how much of the incoming starlight the planet reflects. Tens of billions of potentially habitable worlds in one galaxy. So why is everything so extraordinarily, persistently, almost mockingly quiet? The first thing to understand, and this is genuinely important, not just a technical footnote, is that the phrase habitable zone is significantly more misleading than it sounds. The phrase does not mean a planet is habitable. It does not mean water is present. It does not mean water was ever present. It says nothing about whether the planet has an atmosphere thick enough and composed correctly to keep water in the liquid phase on its surface. It makes no claim about whether the surface temperature actually falls within the range that liquid water requires. It does not address the planet's geological history, its magnetic field, its rotational stability, the activity level of its host star, or 100 other factors that turn out to matter enormously. All the phrase technically indicates is that the orbital distance from the star is not immediately disqualifying that a planet at that distance, if it had the right atmosphere and the right reflectivity and the right surface conditions and the right everything else, could in principle have liquid surface water. The conditions can still be made impossible by any one of dozens of other factors, and very often they are. When you examine the catalogue of actually confirmed exoplanets, rather than just the estimated statistics, most of the discoveries are nothing like Earth. The first planets found around other stars were hot Jupiters, massive gas giants orbiting so close to their host stars that their atmospheric temperatures can reach thousands of degrees and their orbital periods last only a few Earth days. They were the easiest category to detect because their size and proximity to their stars produced the largest, most frequent transit signals. After hot Jupiters came super-Earths, rocky planets larger than our own, often with surface gravities substantially higher than Earth's, frequently orbiting so close to their stars that a full year there might last only a few Earth days. After those came tidally locked worlds, where gravitational interaction with the host star has gradually synchronized the planet's rotation with its orbital period, leaving one hemisphere permanently bathed in starlight and one hemisphere permanently dark and frozen. And then came scorched, airless rocks, planets that once had atmospheres stripped away by stellar radiation, planets with gravity so high that the cardiovascular system of any Earth-like organism would struggle to function, planets orbiting in conditions that preclude chemistry of the kind life as we know it depends on. Out of 6,000 confirmed exoplanets, the number that could be described as roughly Earth-sized, in a roughly appropriate orbit, around a roughly stable and long-lived star, is in the low dozens, a small fraction of a small fraction. Part of the silence, then, has a simple explanation. Most of these worlds were never positioned to produce a signal of any kind, biological or otherwise. They lack the chemistry, the temperature, the atmosphere, the liquid water, or the time. They are stones in space, geologically interesting perhaps, biologically irrelevant. But that accounts for only part of the silence, and not the most important part. The part that is harder to explain is not the silence from worlds that obviously could not host life. It is the silence from worlds that plausibly could have. Even by the most conservative estimates, Earth-like candidate worlds exist in substantial numbers. And from those candidates, the ones that have the right size, the right distance from a suitable star, the right potential for surface water, we have found nothing. No radio signal, no optical beacon, no atmospheric chemical fingerprint we can confidently attribute to biological processes rather than geological ones. Nothing that compels us to conclude that biology is happening or has happened. That is the silence that resists easy explanation. The silence of worlds that, by reasonable statistical logic, ought to have something going on in them. The image I keep returning to when I try to hold this idea, the universe, or at least the portion of it we can observe, is not quiet because it was always empty. It is quiet the way a large public library is quiet after closing time in a building that has been closed for a very long time. The structure is still there. The shelves are still there. Every book has a real author behind it, real thought, real labor, real words that someone organized deliberately. The library was not built empty. People filled it over years and decades, but it has been a long time. The writers are gone, the readers are gone. The lights have been dimming one by one for longer than anyone alive can remember. The building has gone silent. The books remain. The voices that wrote them and read them have not remained. When the Kepler Space Telescope detected a planet during its operational life, what the instrument actually recorded was a star becoming very slightly dimmer at regular, predictable intervals. The dimming occurred when the planet passed between the star and the telescope, blocking a tiny fraction of the starlight that would otherwise reach the detector. That was the entire observation for the vast majority of discoveries. Not the planet itself, not any feature of the planet, a periodic shadow. From the depth and timing of that shadow, astronomers could work out several things: the approximate size of the planet relative to its star, its orbital distance from the star, and the length of its year. What the shadow told them nothing about was the planet's surface, its atmospheric composition, whether it had water, whether it had anything on it at all. The observation identified that something was there. Everything else was inference. This is what the majority of exoplanet science looks like. You stand at an enormous distance from a building and watch the shadows it casts on the ground outside. From the geometry and timing of those shadows, you can infer something about the building's size and shape. You might be able to guess at how many floors it has. What you cannot do, from that distance, and with that limited information, is determine whether anyone ever lived inside it, or whether anyone is there now, or whether the building is in the condition the shadows suggest. The timing problem makes this even more complex. Even granting the hypothetical that every Earth-like world in the galaxy had produced intelligent life at some point in its history, the probability that any two such civilizations would exist and be capable of communication at the same moment within a galaxy whose history spans more than 10 billion years is remarkably low. Consider the mathematics of it concretely. Human radio communication capable of reaching other star systems has existed for roughly 100 years. Something recognizable as human civilization in any form, agriculture, settled communities, the beginnings of recorded knowledge, goes back perhaps 10,000 years. Anatomically modern humans have existed for around 300,000 years. And Earth has been continuously habitable in one form or another for approximately 4 billion years. Compress that 4 billion year habitable history into a single calendar year, starting on January 1st and ending at midnight on December 31st. On that compressed timeline, the entire span of human existence occupies the final 90 seconds before the year ends. Modern scientific civilization, the few hundred years during which we have been capable of systematically studying the universe and developing the technology to send or receive signals across interstellar distances, fits inside the last single second of the year. Now imagine that every other habitable world in the galaxy runs its own version of that calendar. Each calendar starts on a different date. Each runs for a different total length. The brief intervals of civilization, the periods when something on each world would be capable of sending or receiving a signal, are scattered randomly across billions of years of otherwise quiet geological history. The probability that any two of those brief active intervals overlap is low. Most of the time, reaching any particular location at random would locate a world that had not yet developed anything capable of communication, or had developed it and then lost it, or moved past it, or had never developed it at all. The silence is not primarily evidence that nothing exists. It is evidence of timing. It is evidence that existence and contemporaneous existence are two very different things. Astronomers sometimes use a particular phrase, partly with humor and partly in genuine recognition of what the data shows, to describe the experience of listening for signals from the universe. The Great Quiet, not the Great Filter, which is a specific theoretical framework about what prevents civilizations from expanding beyond their home worlds once they develop. The Great Quiet is simpler. It is the observation itself. The receivers are on. The signal level is essentially zero. It has been essentially zero for as long as we have had instruments capable of detecting anything. Some of that quiet may mean nothing was ever out there to transmit. Some of it almost certainly means something was out there once and no longer is. The library is real. The shelves appear to be full. The lights are mostly off. Whether anyone is still inside is a question we do not yet have instruments precise enough to answer, and may not develop those instruments within any time horizon that matters to the people asking the question now. If you want to see what one of those quiet rooms in the library looks like up close, if you want the most concrete, physically accessible example of a world where the conditions arrived and then left, you do not have to travel far from your armchair. We already have one available for inspection. It is the next planet over. Mars is the easiest dead world to discuss, for the simple reason that we can see it with our eyes on the right night. You can step outside, let your eyes adjust to the dark, locate the steady reddish point that does not twinkle the way stars do, because it is a nearby planet reflecting sunlight rather than a distant star generating its own, and there it is, the fourth planet from the Sun, the neighbor, the one that appears as a tangible, visible object in the sky, rather than as an abstraction in a catalogue. For the majority of human history, Mars was a mythological name attached to a wandering point of reddish light. It became a real place in the latter part of the 19th century, when telescopes had advanced to the point of revealing a world with polar ice caps that visibly expanded and contracted with the Martian seasons, and dark surface features that shifted in ways some observers convinced themselves must indicate vegetation responding to seasonal moisture changes. The Italian astronomer Giovanni Schiaparelli reported observing linear features crossing the Martian surface and called them canali channels. The American astronomer Percival Lowell, working from his private observatory in Arizona during the 1890s and early 1900s, concluded those features were artificial canals constructed by an intelligent Martian civilization that was managing the redistribution of water from the polar ice caps to the drying equatorial regions. A dying civilization making desperate engineering decisions to extend its survival on a world gradually losing its water. None of that turned out to be real. The linear features were optical illusions, artifacts of the way the human visual system attempts to impose order and continuity on blurry low-contrast images at the limits of resolution. The dark surface patches were combinations of dust, mineral variation, and topography. There were no canals. There was no civilization managing water resources. The story Lowell told was a projection, a human narrative imposed on ambiguous data. But the underlying intuition that Mars was a dying world, a world that had been something more than it currently was, a world that had been heading towards silence, turned out to be considerably more accurate than anyone at the time could have known. The Mars that exists today is, by any fair scientific accounting, dead. Its average surface temperature is approximately -63 degrees Celsius. That figure is worth sitting with, because for context, the lowest temperature ever recorded anywhere on Earth's surface was measured in Antarctica and reached approximately -89 degrees Celsius during an unusual cold event. The Martian average is roughly comparable to the most extreme cold episodes Antarctica experiences, except on Mars. That brutal temperature is the mean, not the extreme, and the extreme goes significantly colder. The planet's atmosphere is so thin, less than 1% of Earth's atmospheric pressure at ground level, that liquid water placed on the Martian surface would not simply evaporate. It would simultaneously boil and freeze. The pressure is low enough that the liquid phase of water cannot exist at any surface temperature. Water on Mars can be ice or vapor. It cannot be liquid on the exposed surface. If you were somehow standing on the Martian surface in a hypothetical perfect suit that protected you from radiation and temperature, if the suit kept you warm and pressurized and supplied you with breathable air, you would still feel the cold beginning to penetrate the soles of your boots within minutes, because the ground itself is a heat sink at temperatures that drain warmth through contact faster than any suit can fully compensate. The sky above you would not be blue. It would be a pale, dusty butterscotch color, not because of any unusual atmospheric chemistry, but simply because there is not enough air to scatter light in the way a dense atmosphere like Earth's does. The sun would appear smaller than it looks from Earth, and noticeably dimmer. The horizon would feel surprisingly close, because Mars is a smaller world, and the curve of the surface falls away from any standing point faster than it does on Earth. The landscape would be silent in a way that has no good terrestrial analog, no wind strong enough to carry sound effectively, no animal noise, no water, no movement. It would feel, viscerally and immediately, like a place where something used to live. That feeling, it turns out, is physically justified. Here is what the planetary science tells us about the history of that place. Mars once had a magnetic field, a real, functioning, planet-wide magnetic field, generated by exactly the mechanism that generates Earth's field today, a rotating core of molten conductive metal at the planet's center, with the rotation producing a dynamo effect that maintains a dipole magnetic field extending far out into space around the planet. That field acted as a shield. It deflected the solar wind, the constant outflow of charged particles that the sun ejects in every direction across the entire solar system. As long as that shield was operating, Mars could hold on to whatever atmosphere it had accumulated through volcanic outgassing during its formation and early geological history. The shield meant that water on the surface could remain liquid, because there was air pressure sufficient to maintain the liquid phase. The shield meant the sky over Mars was thick enough to behave like what we would recognize as a sky, capable of scattering light, carrying weather, supporting the kind of atmospheric circulation that distributes temperature and moisture across the planet. Then the shield went down. The best current estimates for the timing of the collapse of Mars's global magnetic field, derived from the analysis of ancient magnetic signatures preserved in Martian meteorites and from remote measurements of residual magnetism in the planet's crust made by orbiting spacecraft, placed the event at approximately 3.9 billion years ago. This date has been the subject of ongoing refinement by multiple research groups working from different lines of evidence. A particularly detailed study published in 2023 from researchers at Harvard, subsequently confirmed and elaborated upon by follow-up work through 2025, suggests the field may have persisted somewhat longer than the earlier consensus estimate implied, that the decline was more gradual and the final collapse came later than previously thought. but the fundamental conclusion that has been building for decades remains unchanged. The core of Mars cooled past the point where convection could maintain the dynamo. The dynamo stopped generating the field. The field dissolved. After that, the atmosphere began to bleed away. This did not happen overnight or in any single event. It was a process that unfolded over hundreds of millions of years, slow enough that if you had somehow been standing on the Martian surface watching it happen, you would have detected no change from one century to the next, or from one millennium to the next. The solar wind encountered the top of the atmosphere and gradually stripped away the lightest, most energetic molecules, knocking them one by one up out of the gravitational well and into space. The process is called atmospheric sputtering and escape, and it is calculable. And what the calculations show is that the budget was always negative once the magnetic shield was gone. More atmosphere was leaving than could be replaced by any ongoing geological process. The account was draining, slowly but continuously, and it was never going to refill. Today, the atmospheric pressure on the Martian surface ranges from approximately 1 to 40 millibars depending on elevation and season. Earth's surface pressure is 1013 millibars. Mars has less than 1% of Earth's air pressure at ground level. To find air that thin on Earth, you would need to be approximately 30 kilometers above the surface, roughly 3 times the cruising altitude of a commercial passenger aircraft. That is what Mars offers at ground level. An atmosphere comparable in density to what exists 30 kilometers up in Earth's sky. But none of that tells you what Mars was, and what Mars was is the important thing. Before the magnetic field collapsed, before the atmosphere thinned, before the liquid water disappeared, Mars was a different world entirely. And we know this, not from speculation but from the rocks. The Curiosity rover, which has been operating in Gale Crater since it landed in August 2012, has spent more than a decade in continuous operation driving slowly up the layered slopes of a central mountain within the crater, examining rock formations laid down across different periods of Martian geological history. What those rocks tell, layer by layer, is a story that required most of a decade and enormous amounts of analytical work to fully read. Gale Crater was a lake. Not metaphorically, not speculatively. The evidence is now robust enough to state it as geological fact. The layered mudstones, the river-smoothed pebbles transported from distant highlands, the salt mineral deposits, the clay minerals that require prolonged contact with liquid water to form, all of it converges on the same conclusion. Around 3.8 billion years ago, the region that is now a cold, dry, windswept crater was filled with liquid water, a lake fed by river systems draining the surrounding terrain, deep enough and persistent enough to deposit the sedimentary record we are now reading. The lake did not exist for a brief moment. The mineral evidence suggests it persisted, with some variation and interruption, for something on the order of 700 million years. The most clearly habitable conditions appear to have faded away somewhere around 3.1 billion years ago, though there may have been isolated habitable refugia, subsurface water, perhaps, or localized geothermal environments that persisted somewhat longer. 700 million years number deserves to be stated plainly and then contemplated rather than passed over. Complex life, multicellular life, life of any kind that a non-specialist observer would recognize as more than bacterial scum, has existed on Earth for approximately 600 million years. The Cambrian explosion, the event in the fossil record when animals with hard skeletons and complex body plans first appeared in large numbers, happened roughly 540 million years ago. Mars had a habitable surface environment, complete with liquid water and the conditions capable of supporting chemistry at least as complex as early Earth's, for longer than the entire history of recognizable animal life on our planet, and simultaneously, because this is the part that becomes almost unbearable to sit with during that same period, on Earth, life was not merely possible but already happening. The earliest convincing biological evidence preserved in Earth's rocks appears in formations around 3.5 billion years old. Some more ambiguous and more contested evidence points back as far as 3.8 or 3.9 billion years, which means that for an extended stretch of early solar system history, both planets were running what amounts to the same experiment at the same time. Both had liquid water, both had atmospheres, both had chemical energy available in the form of volcanic activity and hydrothermal circulation. Both had the molecular building blocks that are the preconditions of organic chemistry. On one of them, we know for certain that life got started. On the other, every condition necessary for the same experiment was present. And then, around 3 billion years ago, the conditions on Mars stopped cooperating. The window that had been open closed. The experiment, whatever stage it had reached, lost its laboratory. Which brings us back to the rock in the tube. The Perseverance rover landed in Jezero crater on February 18, 2021. The choice of landing site was not arbitrary. Jezero crater, visible in satellite imagery, shows the unmistakable preserved outline of an ancient river delta, the classic fan-shaped sedimentary formation that develops when water flowing across elevated terrain slows as it enters a standing body of water and deposits the material it has been carrying. The delta is still there, readable from orbit, fossilized in stone. The crater was a lake. The river that fed it flowed in from the highlands to the northwest. Perseverance was designed and deployed specifically to explore that ancient lake delta environment and search for chemical and physical evidence of past biological activity. The rover has been doing that work since it arrived, and in July of 2024 it drilled into a rock that the science team informally designated Ava Falls. The drill extracted a small cylindrical core of rock material, which was sealed into a metal sample tube, given the designation Sapphire Canyon. The scientists examining the data from the rover's onboard instruments noticed something that warranted extended attention. The rock contained small, dark nodules distributed through the fine-grained sediment in specific patterns that did not appear random. Some of the nodules had roughly spherical forms that the researchers described informally as resembling seeds. Others appeared in elongated or irregular clusters that suggested comparison to spotted animal patterns. Chemical and mineralogical analysis of those nodules, conducted using the rover's suite of analytical instruments over the following months, identified them as concentrations of iron phosphate, specifically a mineral form called vivianite, combined with iron sulfide in a mineral form called greigite. The combination appeared in a fine-grained mudstone matrix alongside organic carbon compounds. On Earth, this specific combination of minerals, in this specific type of depositional environment, in these specific spatial arrangements, is produced by a particular category of microbial activity, anaerobic bacteria that extract metabolic energy from their environment by transferring electrons between iron compounds and sulfur compounds. These iron-breathing microbes, as they are sometimes called, are well studied on Earth, and the mineral assemblages they produce as metabolic byproducts are distinctive enough to be considered diagnostic signatures of their activity. The patterns Perseverance documented in the Shayava Falls sample are, by the standards of Earth geology, exactly what you would expect to find as evidence of that kind of microbial life. The formal scientific paper describing this discovery was published in the journal Nature in September of 2025. Following a year of extensive internal and external review involving scientists not affiliated with the Perseverance mission, who were specifically tasked with examining and challenging the interpretation. The authors of the paper, scientists who have devoted significant portions of their professional lives to exactly this kind of search, are measured and cautious in their language in the way that the significance of the finding demands. The phrase they use is potential biosignature. They enumerate alternative explanations in detail. Certain volcanic mineral precipitation processes, water-rock interaction chemistry that does not involve biology, diagenetic changes in the sediment chemistry during burial that could, in principle, produce similar mineral assemblages without requiring any living organisms. They explicitly do not claim to have found evidence of life on Mars. What they claim is that they have found something that, in any terrestrial datalogical context, would be the first thing that the famed terrestrial datalogical biology of bioexcodi ecological, gedicals and biology on Bigol, while our cosicatudi on a pediclock and wetcocks, colleagues, clocks, clikes with go clicks and gone on and luck will we're going to hunt will out of golf west what by how does top it all hop well about how go south that's go raw how the sample tube containing that rock is sitting on the Martian surface right now. It has been sitting there since the summer of 2024. The Mars Sample Return Mission, the international effort to retrieve that tube, and the other samples Perseverance has collected, bring them back to Earth, and subject them to analysis improperly equipped. Earth laboratories, with instruments capable of doing the definitive work that rover instruments cannot, is currently in a state of uncertainty. The mission has been undergoing budget review and architectural reassessment. The original retrieval schedule has slipped. The current working estimate for getting any of those samples back to Earth for analysis is somewhere in the late 2030s, with the caveat that this estimate is itself subject to further revision depending on how the mission's technical and financial challenges are resolved. The most scientifically consequential rock sample in the history of our species is sitting on the surface of another planet, in a sealed metal cylinder, exposed to the Martian wind and the Martian radiation environment, while the people who drilled it and analyzed it and wrote papers about it continue their professional lives and wait for the political and budgetary conditions necessary to bring it home. There is a way of thinking about photographs that has always seemed to me to capture something true about them. Photographs are not so much images of people as images of moments. The person in the photograph continues to age, to change, to accumulate more history. The moment in the photograph does not change. The moment is fixed on the film or the sensor. What you hold in your hand is a fragment of time that has been separated from the human being it depicts. The person moves on. The moment stays where it was. That is what the Shava Falls rock sample represents. Whether or not it turns out to contain evidence of biological activity, it is a fragment of Martian time. A moment captured in stone from a period when that planet was something it no longer is. Perhaps a moment from when something alive was chemically processing those minerals, moving electrons between iron and sulfur compounds, extracting energy from the chemistry of an ancient lake, doing the quiet metabolic work of staying alive in a world that 3 billion years later would be the kind of place we send robots to look for traces of exactly that activity. Or perhaps a moment from when no such activity was occurring and the minerals assembled themselves through processes that required no biology. We genuinely do not know which. The image is real. What the image shows is still being evaluated. There is a particular feeling that comes with going into the attic of a house where someone else used to live. You climb up there expecting nothing of significance: dust, old insulation, abandoned storage, and instead you find a box. Inside the box are photographs of real people, in clothing styles you do not recognize, in rooms you cannot identify, in places you have never been. These are people who walked through the same doorways you walk through, who ate in the same kitchen you eat in, who sat on the same stairs you sit on. Generations before you arrived here, before you knew this address existed, before the house was yours in any sense. They are not your family. They are simply people who were there, doing ordinary human things in the same physical space where you now do your ordinary human things. The weight of that, when you really let it in, is difficult to process. Mars is that attic. You go up there expecting cold and dust and nothing of particular interest, and instead you find an album. The photographs are real. They depict someone you have never met and cannot recognize. The camera that took them stopped working an enormously long time ago. That is the situation we are in. Mars is the obvious dead world, the harder one to genuinely grapple with, because it is actually the more extreme case, and because the implications of its history are in some ways more unsettling, is the planet on the other side of us, the one we fly past in our mental model of the solar system, the one we spend about a week on in school and then file away under too hot, cautionary tale. Next topic. That planet is Venus. We do not engage with Venus the way we engage with Mars. Mars has cultural weight. Mars has rovers with names that get attached to the public imagination. Mars is on the covers of books about the future of human civilization, depicted with domed habitats and suited explorers and the red landscape stretching to the horizon behind them. Mars is the destination. Venus is the warning label. The standard school curriculum account of Venus goes something like this. Venus is the planet closest to Earth in size. It is covered in thick clouds. It has a surface temperature hot enough to melt lead. This is the result of a runaway greenhouse effect caused by too much carbon dioxide in its atmosphere. This is what happens when the greenhouse effect goes wrong. Here is a lesson in atmospheric chemistry. Remember this for the test. And now we will move on to Mars. That account is incomplete in ways that matter more than almost anything else in planetary science right now. Here is what the standard account omits. Venus, by the fundamental planetary specifications, is Earth. Not metaphorically, not approximately, by the numbers that astronomers use to classify and compare planets. Venus and Earth are essentially identical. Venus has approximately 95% of Earth's diameter. It has approximately 81% of Earth's mass. Its density is comparable. It formed at approximately the same time in the early history of the solar system, from the same broad mix of materials in the same protoplanetary disk. It occupies the inner solar system, closer to the Sun than Earth, but not dramatically so. By every standard metric that planetary scientists used for most of the history of the field to define what a sister world means, Venus is Earth's sister world. If you were to show an uninformed person a side-by-side comparison of the basic planetary parameters of Earth and Venus, size, mass, density, composition, orbital distance from the Sun, estimated age, and ask them which one could support life, they would have no principled basis for choosing. The numbers do not indicate which is the living world and which is the dead one. And here is the part that I think genuinely deserves extended time, because it changes what Venus means. Venus may have been habitable, with actual, liquid, surface oceans, for as long as 2 to 3 billion years. This is not a fringe hypothesis or a speculative extrapolation from incomplete data. It is the conclusion of sophisticated, three-dimensional climate modeling conducted by researchers at NASA's Goddard Institute for Space Studies. The relevant work, the Way and Del Genio simulations, published in their initial form in 2016 and refined through subsequent work over the following years, takes what is known about Venus's likely early conditions from planetary formation models, applies what is understood about how Venus's slow rotation rate affects atmospheric dynamics, runs a three-dimensional climate simulation forward through time, and finds that under reasonable assumptions about early cloud cover distribution and how it would respond to changing conditions, Venus could have maintained a stable temperate surface climate, with liquid water oceans persisting at the surface for somewhere between 2 and 3 billion years before conditions crossed a threshold and the system began transitioning toward the state it is in now. 2 to 3 billion years of habitable surface conditions. For comparison, complex multicellular life consisting of more than single cells, life of the kind that a non-specialist looking at a fossil or a living specimen would recognize as something, has existed on Earth for approximately 600 million years. Everything we think of when we think of animals, plants, ecosystems, the biological complexity that makes this planet visually and biochemically striking from the perspective of an outside observer, all of that is compressed into the last 600 million years or so of a 4.5 billion year planetary history. Venus, on this model, had liquid surface oceans for roughly 5 times that span, for longer than every animal that has ever lived on Earth, and every plant, and every fungi, and every complex organism of any kind has had to work with. Venus had a potentially habitable surface environment, while the most complex life on Earth was still microbial. Whether anything biological actually developed in that environment is a question that is, in practice, currently unanswerable. We have no fossils from Venus. We have no surface samples from Venus that could be analyzed in any useful way. The few Soviet landers that successfully reached the Venusian surface and transmitted data back, the Venera program probes of the 1970s and 1980s, survived on average less than 2 hours after landing before the heat and atmospheric pressure destroyed them. The longest surviving lander, Venera 13, transmitted data for slightly over 2 hours. The images it returned before failing showed a flat landscape of fractured basaltic rock under a heavy, dim, yellowish sky. No organisms were visible, no structures, no chemistry that obviously indicated biology, but 2 hours is an extraordinarily short window, and the instruments involved were nowhere near the sensitivity that would be required to detect traces of ancient biochemistry. But the question, when it comes to Venus, is not what exists on Venus now. The surface conditions now would destroy any biological evidence that might have accumulated over the habitable period. The question is, what may have existed there during the multi-billion-year window when conditions may have been suitable? And that question cannot currently be answered, and may never be answerable, because the geological record that would contain the answer has been overwritten by 700 million years of extreme geological violence. Here is what happened to Venus. Somewhere around 700 million years ago, the timing is approximate and the subject of ongoing research, conditions on Venus crossed a threshold. The specific trigger or triggers remain debated in the literature. The most frequently discussed candidates include a large-scale global volcanic resurfacing event, during which the entire surface of Venus was repaved by volcanic activity within a geologically brief period of perhaps 50 to 100 million years, releasing enormous volumes of carbon dioxide that had previously been sequestered in rock. The gradual brightening of the Sun over time, which has been increasing Venus's total solar energy input throughout the planet's history. The possibility of a runaway volcanic outgassing episode that rapidly increased atmospheric carbon dioxide to levels the climate system could no longer balance, or some combination of these factors occurring in close enough temporal proximity to push the system past a tipping point from which recovery was impossible. Whatever the specific trigger, the feedback loop that followed was self-reinforcing in the worst possible way. Water vapor is itself a greenhouse gas. As temperatures at the surface and in the lower atmosphere began to rise, for whatever initiating reason, more water evaporated from the oceans into the atmosphere. The additional water vapor in the atmosphere trapped additional heat. The additional heat drove additional evaporation. More evaporation produced more water vapor, which trapped more heat. The system had crossed into what climate scientists call a runaway greenhouse state, a positive feedback loop with no natural break, where every increment of warming drives more warming in a process that does not stabilize until it has run to completion. The completion, in Venus's case, was the total evaporation of the oceans. Once the ocean water was in the upper atmosphere as vapor, it encountered solar ultraviolet radiation, which has enough energy to break apart water molecules. The hydrogen, being the lightest element, and therefore the fastest moving at any given temperature, gradually escaped the planet's gravitational field and drifted into space. The oxygen, being heavier and more chemically reactive, mostly bonded with surface minerals and was incorporated into rocks. The carbon dioxide that had previously been dissolved in ocean water and locked into carbonate rocks through geological cycling was now free in the atmosphere and had no ocean to be reabsorbed into. The atmospheric carbon dioxide concentration grew. The greenhouse effect intensified. The system reached its new equilibrium state. That state is what Venus is today. The average surface temperature is approximately 462 degrees Celsius. For reference, lead melts at approximately 327 degrees Celsius. The surface temperature of Venus exceeds the melting point of lead by a margin of about 135 degrees, and the temperature is fairly uniform across the entire surface because the thick, circulating atmosphere efficiently distributes heat even between the day and night sides. The atmospheric pressure at the surface is approximately 92 times Earth's atmospheric pressure. The equivalent pressure on Earth is found at a depth of roughly 900 meters below the ocean surface, far beyond the operational depth of any crewed submarine. The Soviet landers that survived on the Venusian surface for those brief periods before being destroyed were essentially deep-sea pressure vessels built with hulls thick enough to resist the crushing atmospheric weight, adapted for an environment that should not, by any intuitive understanding of what a planet can be, exist at a planetary surface. The cloud layer that covers Venus is composed of sulfuric acid droplets. Those clouds do produce rain. The rain never reaches the surface. The lower atmosphere is hot enough that liquid sulfuric acid evaporates before it can fall from the cloud layer to the ground. The sky has weather. The weather produces acid precipitation. The acid precipitation evaporates back into the clouds it fell from, cycling perpetually in the upper atmosphere, never landing anywhere. That is Venus. That is what a potentially habitable world looks like after the runaway feedback runs to completion. Now here is the detail that, for me, gives this the weight it deserves. The oceans that evaporated off Venus billions of years ago are not simply gone without trace. They left a fingerprint. If you measure the hydrogen in Venus's upper atmosphere, with instruments sensitive enough to distinguish between different isotopes of hydrogen, you find something anomalous. There are two stable isotopes of hydrogen, ordinary hydrogen, with a nucleus containing a single proton, and deuterium, or heavy hydrogen, with a nucleus containing 1 proton and 1 neutron. On Earth, deuterium is rare. It makes up approximately 1 part in 6,400 of the hydrogen in Earth's oceans. On Venus, the ratio of deuterium to ordinary hydrogen in the atmosphere is approximately 150 times higher than it is on Earth. A factor of 150 is not a small measurement uncertainty. It is not a calibration artifact. It is a real, robustly measured, physically significant number, and there is only one coherent physical explanation for it. Lighter particles move faster at any given temperature than heavier particles. This is a direct consequence of the physics of thermal motion. When hydrogen atoms or molecules are in the upper atmosphere of a planet and are struck by solar wind particles or energized by ultraviolet radiation, the probability of any given atom or molecule escaping the planet's gravitational field is higher for lighter particles than for heavier ones, because the lighter particles are already moving faster. Ordinary hydrogen, being lighter than deuterium, escapes preferentially. If you start with a planet that has water, which contains both ordinary hydrogen and deuterium in whatever initial ratio they arrived with, and that water evaporates into the upper atmosphere over billions of years and is then gradually broken apart and lost to space, the ordinary hydrogen escapes faster than the deuterium. Over billions of years, the remaining hydrogen in the atmosphere becomes progressively enriched in deuterium relative to the initial ratio. When you measure Venus's atmosphere today and find deuterium enriched to 150 times Earth's ratio, you are not measuring a chemical curiosity. You are measuring the chemical residue of an ocean's worth of water that evaporated into space billions of years ago. The ordinary hydrogen is gone. The deuterium, being heavier and slower to escape, has accumulated in the remaining atmosphere. What you are looking at in the spectrometer data is the isotopic signature of a lost ocean, the fingerprint of water that existed and then didn't. The water is gone. The record of the water is not. There is, I think, a kind of grief in that detail, when you let yourself sit with it, rather than just filing it away as interesting planetary science. We do not usually attribute anything like grief to planetary processes, but there is something about the idea of an ocean's worth of water leaving behind only a ratio of isotopes in a poisoned atmosphere. Something about the idea of being able to read the obituary of an ocean from a spectrometer printout while the planet where that ocean once existed glows at 462 degrees, that resists being processed as merely a factual datum. Venus's ocean is gone. The shape of where it was is still there, measurable, real. The shape of an absence, and importantly, this kind of measurement is not limited to Venus. With sufficiently sensitive instruments pointed at sufficiently close exoplanets, we could in principle measure deuterium enrichment in the atmospheres of planets orbiting other stars and identify worlds that once had abundant water and no longer do. The James Webb Space Telescope and the generation of extremely large ground-based observatories being constructed and planned for the late 2020s and 2030s will expand our atmospheric measurement capabilities for nearby exoplanets substantially. The first time we detect a Venus-like deuterium signature in the atmosphere of an exoplanet, we will not be discovering something unexpected. We will be confirming what the physics of planetary evolution already strongly implies, that there are worlds out there with this same fingerprint, this same chemical ghost, this same record of a lost ocean in an atmosphere that used to be something else entirely. Venus's porch light is still on, in the sense that the sun shines on it. The light has been on for 4 billion years. The house burned down from the inside. So we now have 2 dead worlds in our own neighborhood, 1 solar system, 3 rocky inner planets, one currently alive, two already dead, by completely different mechanisms, through completely different sequences of events, across different timescales, but ending in the same fundamental category of outcome. Worlds that are no longer habitable for any form of life we can currently conceive of. Mars was killed primarily by the cooling of its core. When the core cooled past the point where convection could maintain the dynamo, the magnetic shield dissolved. Without the shield, the atmosphere bled away over hundreds of millions of years into the solar wind. Without the atmosphere, the water could not remain liquid. Without the liquid water, the surface became the cold, dry, radiation-exposed desert it is today. The death came from the inside, from the planet's own interior cooling and becoming inert. Venus was killed primarily by a runaway atmospheric feedback. The precise trigger remains debated, but the mechanism once triggered was self-reinforcing. Rising temperatures drove more evaporation, which drove more warming, which drove more evaporation, until the oceans were gone and the atmosphere had accumulated to the crushing, burning density it maintains today. The death came from the outside and from the atmosphere, from a feedback system that crossed a threshold and could not be reversed. Different causes, same result. Two planets the same age as Earth, built from the same materials, starting with the same broad set of conditions, one in the dust, one in the fire, Earth between them, which raises the question that should make anyone who thinks about it for more than a moment genuinely uncomfortable. What does it mean that both of Earth's neighboring rocky planets have already lost their habitability by completely different mechanisms, while Earth has maintained it? Is Earth genuinely different in some fundamental way that makes it more stable? Or is Earth simply at a different point in the same long arc of eventual loss? To answer that honestly, we have to look at something that most public discussions of the habitable zone treat as a fixed background condition, when it is actually a continuously moving target. The mental model most people carry around of a habitable zone is something like this. There is a ring around every star. The ring is the right distance from the star for liquid water to exist on a planet's surface. Planets inside the ring are habitable candidates, and planets outside the ring are not. Earth is comfortably inside the ring, and this explains in broad terms why we are here. The ring is stable. The ring persists. The conditions inside the ring are reliable over the long term. Almost none of that is accurate. The habitable zone is a real concept with rigorous mathematics underlying it. It does describe the range of orbital distances from a star at which liquid water could, in principle, exist on a planetary surface, given certain baseline assumptions about atmospheric properties and surface reflectivity. For our Sun in the current epoch, the commonly used estimates place the habitable zone's inner boundary at approximately 95% of Earth's current orbital distance and the outer boundary at roughly 170% of it, though different models using different assumptions about cloud cover and atmospheric composition give somewhat different specific numbers. But the habitable zone moves. It is not fixed. It is not a permanent feature of a star system. It shifts as the star evolves, and stars evolve continuously over their lifetimes. Main sequence stars, the category that includes our Sun, and the majority of stars in the galaxy at any given moment, generate energy by fusing hydrogen into helium in their cores. As fusion proceeds over billions of years, the helium accumulates in the core. The core gradually becomes denser. The increased density raises the pressure and temperature within the core. The higher temperature causes the fusion rate to increase slightly. The increased fusion rate means the star outputs slightly more energy. Year by year, this effect is unmeasurable. Over billions of years, It adds up to a substantial change in the star's luminosity. Our Sun has brightened by approximately 30% since Earth formed 4.5 billion years ago. To put that in visceral terms, if the Sun today were emitting only as much energy as it emitted when Earth was forming, the surface temperature of Earth would be cold enough for the oceans to freeze solid and for the planet to be locked into a permanent glaciated state. There is geological evidence of liquid water on Earth's surface dating back at least 4 billion years, and possibly as far as 4.4 billion, a discrepancy that planetary scientists call the faint young sun paradox and explain through a combination of a much thicker early greenhouse atmosphere, different surface properties, and possibly different rates of tidal heating. The resolution of the paradox matters less here than the underlying point. The Sun has brightened substantially over the planet's history, and it continues brightening. The current rate of solar luminosity increase is approximately 10% per billion years. That sounds slow. At the scale of human experience, geological processes always sound slow. But when applied to Earth's climate system, the consequence is not slow at all in geological terms. As the Sun brightens, the habitable zone, the ring of appropriate orbital distances, shifts outward. The inner boundary of the zone, the line inside of which incoming solar energy would be sufficient to trigger an irreversible atmospheric warming cascade, similar to what occurred on Venus, moves further from the Sun with time. Earth currently sits well inside the habitable zone, with the inner boundary positioned closer to the Sun than we are. But the inner boundary is moving toward us. In approximately 1 billion years from now, the specific estimate varies by a few 100 million years depending on which climate model you use and what assumptions you make about future carbon dioxide cycling and cloud feedbacks. The inner boundary of the habitable zone will reach Earth's orbital distance. That does not mean Earth becomes instantly uninhabitable the moment the inner boundary reaches us. The process is gradual. As solar energy input increases, surface temperatures rise incrementally. Higher temperatures cause more water to evaporate into the upper atmosphere. Water vapor in the upper atmosphere is broken apart by ultraviolet radiation into its component, hydrogen and oxygen. The hydrogen, being light, gradually escapes to space. The oceans, slowly, over millions of years, begin losing water volume. As the oceans shrink, the water cycle that currently regulates climate and distributes nutrients across the biosphere weakens. As surface temperatures continue to rise, the conditions required by complex multicellular life become progressively harder to maintain across larger and larger fractions of the planet's surface. Most serious climate models that have addressed this question converge on a window of approximately 1 to 1.5 billion years before. Surface conditions on Earth become incompatible with the survival of complex multicellular life. This does not mean microbial life ends immediately at that point. There are organisms alive on Earth right now that thrive in superheated water near deep ocean hydrothermal vents, in highly acidic or alkaline environments, in subsurface rock formations kilometers below the surface, in conditions that would rapidly kill any more complex organism. Some version of microbial life might persist on Earth for hundreds of millions of years beyond the point where surface conditions become untenable for everything else. Earth's biological history might close the way it opened, with single-celled organisms in extreme environments, quietly doing their chemistry in the dark, without access to anything resembling a sky worth looking at. Push further into the future. In approximately 3 to 4 billion years from now, Earth's surface temperatures will be high enough that the oceans have largely evaporated. The water cycle that drives plate tectonics, the subduction of water-bearing oceanic crust back into the mantle, begins to fail. The geological recycling of carbon dioxide between the atmosphere and the surface rock that has kept Earth's carbon cycle in approximate balance for billions of years and prevented Venus-style runaway warming from occurring here begins to slow. Earth, by this point in its future, would be largely unrecognizable. The continents would still exist in some form, but the landscape they support would bear no resemblance to anything a present-day human being could navigate or recognize. In approximately 5 billion years from now, the Sun will exhaust the hydrogen fuel available in its core and begin transitioning from its main sequence phase to its red giant phase. The core will contract in heat. Hydrogen fusion will continue in a shell surrounding the contracting core. The outer envelope of the Sun will expand dramatically. The Sun's surface will cool slightly, even as its total energy output increases enormously due to the vastly increased radiating surface area. Mercury will be swallowed. Venus will be swallowed. Modeling of Earth's fate during this process, accounting for the gradual loss of solar mass during the red giant phase and the resulting change in Earth's orbital distance, and also accounting for the tidal interaction between Earth and the expanding solar envelope, produces a range of outcomes. Some studies find that orbital migration outward as the Sun loses mass might allow Earth to narrowly escape the expanding solar atmosphere, leaving behind a scorched, airless, waterless remnant, orbiting a cooling stellar remnant. The central estimate from the most detailed recent modeling is that Earth does not escape that tidal drag from the expanding solar atmosphere, pulls Earth inward, and the planet is consumed somewhere around 7.5 billion years from now. So Earth has two relevant future dates. The first, approximately 1 to 1.5 billion years from now, when the surface conditions that support complex multicellular life become untenable. The second, approximately 7.5 billion years from now, when the planet itself is most likely consumed by the expanding Sun. Earth has been habitable for approximately 4 billion years. Earth has approximately 1 to 1.5 billion years of habitable surface conditions remaining before the first threshold is crossed. The total habitable window for this planet, from its beginning to that first threshold, is somewhere between 5 and 5.5 billion years. We are approximately 4 billion years into that window. We are past the midpoint. The largest portion of Earth's life-bearing history is already behind us. The window is not closing imminently, on any timescale that is relevant to any individual human life, or to any civilization that might exist for thousands or even tens of thousands of years. The window will remain open, but on the timescale of the planet itself, on the timescale we are using when we ask how long Earth gets to be a habitable world, we have already used most of it. Earth is not in the morning of its habitable history. Earth is in its late afternoon. The evening has not begun, but it is coming. The ending is not imminent by any human measure, but it is closer than the beginning. This image comes to me when I try to hold all of that simultaneously. There is a kind of evening that happens in particular seasons, in particular places, when the temperature that has been oppressive all day finally begins to relent as the sun gets lower. The air cools just enough to be comfortable for the first time in hours. The light shifts from white and harsh to golden and horizontal. The sounds of the day, the heat, insects, the wind, the activity of animals seeking shade, change to the sounds of the cooling evening. And you know, because you have lived through enough of these days, that the dark is coming. The temperature will keep dropping after the light goes. The comfortable window between too hot and too cold is brief. It will close, but it is not closed yet. Right now, in this particular moment, the window is exactly right. That is the moment Earth is in. The window is open. The conditions are right. The oceans are still liquid. The air is still breathable. the magnetic field is still functioning. The carbon cycle is still in approximate balance. The sun is still within the range where it provides enough energy for photosynthesis without providing so much that it drives the system past a tipping point. The planet is doing what planets only get to do during a bounded portion of their existence. We are inside that window. The window will close. Both of those are true simultaneously, and neither cancels the other out. There is something I want to spend more time on before going further, because it connects to everything that follows and changes the question in ways that are easy to miss if you move past it too quickly. We have been talking, so far, primarily about conditions, about what a world needs to be habitable, about how habitable windows open and close, about what happened to Mars and Venus when their conditions crossed the wrong thresholds. We have been treating habitability and life as though they are closely linked, as though a world with the right conditions for long enough will naturally produce life. That assumption is worth examining directly, because it may be wrong. Habitability is a description of conditions. It is a statement about what is chemically and physically possible on a given world at a given time. Life, the actual presence of biological organisms, of self-replicating chemistry, of metabolism and reproduction and evolution, is a description of what is actually happening. Those two things are not the same thing. They are not even very close to the same thing. We have exactly one confirmed example of a world that was both habitable and actually inhabited by life. That world is Earth. One example, and one example, in any empirical science, tells you almost nothing about the underlying frequency of the phenomenon you are studying. You cannot derive a reliable probability from a single data point. You can only say, it can happen. It happened here. The probability is somewhere between 0 and 1. You cannot say anything more specific than that, from the data available to you. What we know about the origin of life on Earth is this. Earth had liquid surface water for somewhere between 100 million and 700 million years before there is any clear evidence in the geological record of biological activity. The range reflects genuine uncertainty about both when Earth's oceans first stabilized into a consistent liquid water environment and when the first organisms appeared. Estimates for the formation of the early oceans range from approximately 4.4 billion years ago to about 4 billion years ago, depending on which geological evidence you weight most heavily. Estimates for the earliest clear biological signatures range from approximately 4 billion years ago to about 3.5 billion years ago. So, somewhere between essentially zero time and 700 million years passed between Earth being a habitable world and Earth being an inhabited world. We do not know where in that range the real answer lies. Was life nearly instantaneous, appearing within a geologically brief interval after conditions permitted, with the apparent gap between habitability and confirmed biology simply reflecting the incompleteness of the very ancient rock record? Or did the origin of life require hundreds of millions of years of increasingly complex prebiotic chemistry cycling through many iterations before something finally self-sustained and replicated? The answer to that question is probably the most important unanswered question in all of biology, and possibly in all of science, and we do not currently have a good answer. What we can do is think carefully about what the origin of life actually requires, and try to assess how probable those requirements are. The transition from non-living chemistry to a self-sustaining, self-replicating, evolving biological system requires, at minimum, some mechanism for storing heritable information, something analogous to DNA or RNA, capable of encoding instructions that persist and can be transmitted. Some mechanism for translating that stored information into functional molecules, something analogous to proteins, capable of carrying out the chemistry that the stored instructions specify. Some system for enclosing the information, storage, and translation machinery within a defined boundary, something analogous to a cell membrane, capable of maintaining a distinct chemical environment inside versus outside. An energy source capable of driving the chemistry continuously, and a replication mechanism that produces copies of the entire system with an error rate low enough that the copies are functional, but high enough that variation can accumulate and evolution can operate. All of those things need to be present in forms that are compatible with each other, in an environment that is compatible with all of them, with enough time and the right conditions for them to assemble. None of it is trivial. The probability estimates for this process occurring, derived from different starting assumptions about prebiotic chemistry, differ by many orders of magnitude between different serious researchers who have spent careers thinking about the problem. There are distinguished biochemists and origin-of-life researchers who believe the assembly of the first self-replicating system from prebiotic chemistry is so improbable, requiring such a specific combination of molecular structures assembling in the right configuration, that it may be a near-unique event in the history of the observable universe, something that happened here by extraordinary statistical chance, and may not have happened anywhere else, or may have happened only a handful of times across the entire billion-year history of the galaxy. There are equally distinguished researchers who believe the same process is so chemically favored, so strongly driven by the thermodynamics of the available chemistry in the right environment, that it should occur within a geologically brief interval on any planet with liquid water, the right temperature range, and the right elemental abundances, something that is, in a sense, almost inevitable given the right conditions. Both groups are working from the same limited data. Both groups include scientists with impressive track records in adjacent disciplines. They disagree not because one group is wrong and the other is right, in ways we could currently adjudicate, but because the problem is genuinely unsolved, and the evidence is genuinely insufficient to resolve it. The origin of life is among the hardest scientific questions currently open, and unlike many difficult scientific questions, we do not yet have a clear experimental path toward resolving it. The implication for the broader question we are sitting with tonight is stark. Even if Mars had liquid water for 700 million years, longer than the entire history of complex animal life on Earth, that does not tell us whether life appeared there. A habitable world is necessary for life. It is not sufficient. The conditions could have been perfect throughout that entire window, and nothing biological might ever have assembled. Or something might have assembled very early in the window, persisted for a long time, and then ended when the window closed. Or something might have assembled briefly and failed. We cannot know from orbit. We cannot know from rover data. The tube with the potential biosignature is the closest we have come to any evidence that bears on the question. And even the tube, even if it comes home, and even if the laboratory analysis confirms biological activity, tells us only that life appeared on Mars. It says nothing about how likely or common that appearance was. We would have two data points, Earth and Mars, both from the same solar system, both from the same general region of the same galaxy, and we would still be trying to derive a general rule from an absurdly small sample. Habitability is the soil. Whether a seed lands in the soil, and whether that seed germinates, and whether the resulting organism survives long enough to matter. Those are separate questions that the soil conditions cannot answer. The question of the origin of life connects naturally to one more dimension of this problem that changes the picture significantly when you fully absorb it. Even if life appears commonly on habitable worlds, even if abiogenesis is as favored as the most optimistic researchers believe, life still has to survive, and survival, the long-term persistence of life through the geological and astronomical changes that every planet experiences over billions of years, turns out to be far from guaranteed, even on the planet that is currently our best-known success story. Earth's own history contains multiple events where the continuation of life here came genuinely close to failing. The fossil record, which preserves a necessarily incomplete but still informative record of what was alive at different points in planetary history, documents 5 major mass extinction events, each representing an interval during which such a large proportion of existing biological diversity disappeared in a geologically short time that the rock record itself becomes thin and sparse. You can read the paleontological literature covering a major mass extinction event and find that the relevant material fits in a brief section of a textbook, not because the event was small, but because the event so dramatically reduced the diversity of life that there is simply less fossil evidence for that period. The diversity was not there to leave evidence. The 5 major mass extinction events, documented in the Phanerozoic fossil record, the period of Earth's history, for which we have sufficiently abundant and diverse fossil material to see these events clearly, are the Ordovician-Silurian extinction, approximately 444 million years ago, which eliminated around 85% of the marine species present at the time. The late Devonian extinction, approximately 372 million years ago, eliminating roughly 75% of species. The Permian-Triassic extinction, approximately 252 million years ago. The Triassic-Jurassic extinction, approximately 201 million years ago, and the Cretaceous-Speleogene extinction 66 million years ago, which ended the non-avian dinosaurs and which most people learn about in childhood. Of these, the Permian-Triassic event stands apart from the others in scale. It is sometimes called the Great Dying by paleontologists, and the numbers justify the name. Approximately 96% of all marine species present at the time went extinct. Approximately 70% of terrestrial vertebrate species went extinct. Insects, which are, as a class, extraordinarily resistant to mass extinction, having survived every other extinction event in the fossil record, experienced the only mass extinction in their entire evolutionary history during the Permian-Triassic event. The fossil assemblages on either side of the geological boundary marking the event are so different that examining them without context, you would reasonably conclude you were looking at the records of 2 entirely different planets. The recovery from the Permian-Triassic extinction required between 5 and 10 million years before ecological diversity approached pre-extinction levels. 5 to 10 million years, during which the biosphere was, in some genuine sense, operating on emergency reserves. Life on Earth was not gone during that interval. The microbes, the surviving lineages of larger organisms, the ecological systems rebuilding around what had survived, but the richness and complexity of the biosphere had been reduced to a fraction of what it had been, and rebuilding that complexity took longer than modern humans have been a distinct species. That is the worst extinction event in the well-preserved fossil record. But it is not the worst extinction event in Earth's history. The worst one happened so far back in time that it is barely represented in the fossil record at all. It affected single-celled organisms in shallow seas more than 2 billion years before the Permian-Triassic event, and it has no dramatic asteroid impact to anchor it in popular imagination, no named geological boundary that most educated people have heard of. It is called the Great Oxidation Event, and it is the strangest catastrophe in the history of life on Earth because it was not caused by any external agent. It was not an asteroid, or a flood basalt volcanic episode, or a change in solar luminosity, or a nearby stellar explosion. It was caused by life itself, by a specific group of microorganisms learning to do something metabolically novel that turned out to be, from the perspective of most of the life then existing on Earth, catastrophically toxic. For approximately the first 2 billion years of life's existence on this planet, roughly half of the total 4 billion year history of life on Earth, the dominant organisms were anaerobes, organisms that extracted energy from chemical reactions not involving oxygen. There was no free oxygen in the early atmosphere. The atmosphere was composed primarily of nitrogen, carbon dioxide, methane, water vapor, and various trace gases. Oxygen was absent from the atmospheric mixture because elemental oxygen is highly reactive and tends to bond with other available elements wherever it appears, and nothing in the early biosphere was producing it in significant quantities. Then, sometime before 2.7 billion years ago, a group of microorganisms evolved what we now recognize as oxygenic photosynthesis, the ability to use sunlight energy to split water molecules, combining the resulting hydrogen with carbon dioxide to produce organic compounds, and releasing molecular oxygen Frio as a metabolic byproduct. These organisms, the ancestors of modern cyanobacteria, were not trying to change the world. They were simply doing what living organisms do, finding an available energy source and exploiting it. The available energy source, in this case, was sunlight. The available electron donor was water. The byproduct was oxygen. Initially, the oxygen produced by these organisms was absorbed almost immediately by chemical reactions with the dissolved iron and other reduced compounds in the early oceans. The oceans acted as a vast sink, consuming the oxygen nearly as fast as the microbes produced it. The geological record of this period survives in the form of banded iron formations, those alternating red and dark, sedimentary sequences found in ancient rock formations in places like Western Australia and the Canadian Shield, which represent the oxidized iron that precipitated out of solution as rising oxygen levels forced the dissolved iron out of solution as iron oxide. But the sinks were finite. The dissolved iron was gradually consumed by this process. The other reduced compounds in the oceans that had been absorbing oxygen were progressively used up. As the capacity of the oceans to absorb newly produced oxygen reached its limit, oxygen began accumulating in the atmosphere. The concentration of atmospheric oxygen began rising, slowly at first, then more rapidly. By approximately 2.4 billion years ago, the concentration had reached levels sufficient to leave an unambiguous geochemical signature in the rock record. This is the Great Oxidation Event. For the anaerobic organisms that had spent 2 billion years building the entire biosphere of early Earth into what it was at that time, the rising oxygen concentration was not a minor environmental perturbation to be adapted to. It was an existential catastrophe. Molecular oxygen is chemically aggressive. For organisms whose metabolic chemistry had evolved in its complete absence, oxygen was not a resource, it was a poison. It attacked the cellular machinery. It disrupted the chemical pathways those organisms depended on for energy. It was lethal. The Great Oxidation Event killed an estimated 80 to 99% of all life on Earth. The range reflects the genuine uncertainty inherent in trying to estimate biological mortality from a fossil record that, at that age and for single-celled organisms, is inevitably incomplete. But the genomic evidence, the geochemical evidence, and what fossil record exists all converge on the same conclusion. The first oxygenation of Earth's atmosphere constituted a mass extinction event that dwarfs anything in the Phanerozoic fossil record, in both the percentage of life eliminated and in the absolute span of biological evolution that was terminated. The first mass extinction in the history of life on Earth was not caused by a rock falling from space. It was not caused by volcanic eruptions. It was not caused by any change in the solar luminosity or orbital dynamics or any other external factor. It was caused by life itself learning a new metabolic trick, releasing a molecule that turned out to be toxic to most of the biology that preceded it. Life nearly destroyed itself by inventing the chemistry that makes our existence possible. Consider what that means. Everything you have inhaled today, the oxygen that is sustaining your brain function, your cardiovascular system, every cellular process in your body that depends on aerobic metabolism, that oxygen is part of the same atmospheric chemistry that 2.4 billion years ago was a planetary-scale catastrophe for most of the life then existing on Earth. The molecule you required to remain conscious was, for 2 billion years of Earth's history, absent from the atmosphere. When it appeared at significant concentrations for the first time, it killed the vast majority of the organisms alive at that moment. The reason you were able to breathe it without dying is that your evolutionary lineage descends from organisms that survived the catastrophe and over hundreds of millions of years evolved the metabolic machinery to exploit oxygen as an energy source rather than being destroyed by it. The biological complexity that makes animal life possible, the energy-intensive metabolism, the sophisticated cellular machinery, the ability to build and maintain complex multicellular bodies, all of that depends on aerobic respiration, on the ability to extract large amounts of chemical energy from oxygen. None of it could exist without the great oxidation event. None of it could exist if life had not nearly destroyed itself by inventing photosynthesis. The recovery from the great oxidation event was neither quick nor straightforward. Between the oxygenation of the atmosphere around 2.4 billion years ago and the appearance in the fossil record of the first convincingly complex multicellular organisms lies approximately 1 billion years of geological history that paleontologists have come to call the boring billion. The name captures something real about what the rock record from that period looks like. Microbial life is present throughout it. Chemistry is happening. The world is not lifeless, but the variety, the complexity, the innovation visible in the record is dramatically lower than what preceded and followed it. The biosphere spent 1 billion years recovering from the catastrophe and reorganizing around the new atmospheric chemistry before producing anything more complex than microbial films and mats. 1 billion years for perspective, that is more time than has passed since the Cambrian explosion, the event usually cited as the beginning of complex animal life. Eventually, single-celled organisms developed the metabolic machinery to use oxygen efficiently rather than be destroyed by it. Eventually, eukaryotic cells appeared, cells with the internal membrane-bound compartments and complex structural organization that distinguished them from the simpler prokaryotic cells that had dominated the first 2 billion years of life's history. Eventually, eukaryotic cells began organizing into multicellular bodies. Eventually, those multicellular bodies became complex enough to leave clear traces in the fossil record. Eventually, the Cambrian explosion happened, and the diversity of animal life began the trajectory that led, after another 540 million years of evolutionary history, to the specific branch of vertebrates, and then mammals, and then primates, and then hominids, and then anatomically modern humans, that makes this conversation possible. The chain that leads here required the Great Oxidation Event. The Great Oxidation Event nearly ended the chain before it could lead anywhere. What all of this implies for the question of life elsewhere is both straightforward and unsettling. If life on Earth, on the one world we treat as the success case, has come as close to comprehensive elimination as it has, multiple times, and once came close because of life's own chemical invention, then what does that suggest about the probability of life elsewhere having navigated equivalent crises successfully? Every world that develops photosynthesis or its chemical analog will produce some version of the oxygen crisis, or an analog to it, as a byproduct. What percentage of those worlds contain enough biological diversity and enough chemical buffering capacity to survive the transition? What percentage get the timing right, having had enough time to diversify before the crisis hits, without having the crisis hit so fast that the biology has no time to adapt? We have one example that survived. We have no examples of failures to compare it to, but the survival on Earth was, by the evidence, not a foregone conclusion. It was close. Every world with internal geological activity will experience volcanic episodes of varying intensity. Some of those episodes will be modest enough that life adapts. Some may be intense enough, as the Permian-Triassic event suggests is possible, to eliminate most of what exists, on a world where the initial biological diversity is lower, or the geological setting is different, or the timing relative to the evolutionary history is less favorable. A comparable event might not leave 4% of species to rebuild from. Every world orbiting a brightening star will eventually face the same slow drift of the habitable zone that Earth faces. Whether biology on that world persists long enough to face that drift, and whether it has developed enough complexity by then to matter in any sense we would recognize, depends on a chain of contingent events stretching back to the origin of life on that world. The conclusion is not that life is impossible elsewhere, or even that it is necessarily rare. The conclusion is that the path from habitable conditions to complex, persistent, long-lived biology is narrower and more hazardous than it appears when you look only at the success story. Earth is the success story, and Earth's path to this moment included at least one event, the Great Oxidation Event, where the outcome could plausibly have been different. There is one more dimension to this that I want to spend real time on, because it reshapes everything else and is easy to overlook. When you look at the night sky on a clear night in a dark location, you are not seeing the universe as it currently exists. You are seeing a record, an archive. Every photon of light reaching your eye has been traveling across space for some amount of time before arriving, and that travel time ranges from fractions of a second to billions of years, depending on the distance to the source. The moon you see is a little over a second old, meaning the light you are seeing left the lunar surface about 1.3 seconds ago. The sun you see is approximately 8 minutes and 20 seconds old. The nearest star beyond our Sun, Proxima Centauri, is about 4.24 light-years away. The light currently reaching Earth from Proxima departed in approximately 2021 or 2022, depending on precisely when you are reading this. The North Star, Polaris, is roughly 430 light-years away. The light you see from it tonight left Polaris approximately when Galileo Galilei was a young man, before the telescope had been invented. The bright stars of the familiar constellations span a range of distances from roughly a dozen light-years to a few thousand. Their light represents snapshots of those stars from various points in the past. The center of the Milky Way is approximately 26,000 light-years away. The light you see from the galactic core on a clear night left approximately 26,000 years ago, when the last ice age had not yet ended, before agriculture existed, before any civilization in the current sense had developed. The Andromeda Galaxy, the nearest large galaxy to the Milky Way and visible to the naked eye, under appropriately dark skies as a faint smudge, is approximately 2.5 million light-years away. The light reaching your eye from Andromeda tonight left that galaxy before anatomically modern humans existed on this planet. Our ancestors at the time that light departed were something other than what we are now. The most distant galaxies imaged by the James Webb Space Telescope sent their light when the universe was less than 5% of its current age, over 13 billion years ago. The universe that exists now has had more than 13 billion years of additional evolution since that light departed. Whatever those early galaxies look like today, if they exist in recognizable form at all, is information that has not yet reached us and will not reach us for an enormous span of time. The night sky is, in the most literal physical sense, a historical archive. Every point of light is a message sent at a specific time in the past. The messages are all arriving now, simultaneously at your eye, but they were not sent simultaneously. Some were sent recently. Some were sent during the Bronze Age. Some were sent before the first writing systems existed. Some were sent before multicellular life had appeared on Earth. The sky you see in a single glance spans 13 billion years of history compressed into one simultaneous visual experience. This has an immediate and important implication for the search for life. Suppose we detect an atmospheric chemical signature on an exoplanet that is consistent with biological activity. The planet is 1,000 light-years away. The light we used to detect that signature left the planet 1,000 years ago. The atmosphere we measured is 1,000 years old. If that planet had a technological civilization that reached our current level of technological development 2,000 years ago, and then experienced a catastrophic collapse 500 years ago, the signature we detect today might be from the period when the civilization was flourishing, and we would be interpreting it as evidence of a currently living world, when in fact we would be looking at the light of a world that has been dead for 500 years. We would not be able to know the difference. We would have no way to know the difference. The information simply has not arrived yet. If the planet is 10,000 light-years away, the atmosphere we measure is 10,000 years old. A civilization that rose and fell within that period, a span shorter than recorded human history, might leave a biological signature in the atmospheric record that we detect today from its peak. Even if the biosphere itself has collapsed in the interim, the news of the collapse is still in transit. It has not arrived yet. It will not arrive for thousands of years. The concept of now becomes genuinely problematic at these distances. What is happening on a world 10,000 light-years away right now, in the sense of simultaneously with this moment on Earth, is information that will not reach us for 10,000 years. We cannot ask what any distant world is doing now. We can only ask what it was doing when the light we are currently receiving left it. Whether anyone is out there now is a question that, for any distant world, cannot be directly answered. We can only determine whether anyone was there, and when. The universe is a postal system with extremely long delivery times and no expedited shipping. Every observation we make is the delivery of a letter that was sent long ago. Some letters are from senders still active. Some are from senders who have moved. Some are from senders who have been gone for longer than any civilization has existed. We cannot tell which is which from the envelope. We can only read the letter and try to date it and try to infer something about the sender's situation at the time of writing. This means that when we search for signs of life in the universe, we are not primarily asking the question we think we are asking. We think we are asking, is there life out there? But the question we are actually able to investigate is, was there life out there at the time this light left its source? Those are different questions. They might have the same answer, or they might not. We have no way, from a distance of light years, to determine whether they have the same answer for any specific world. The universe might not be empty of life. It might be full of worlds where life happened, persisted for some span of geological time that might be brief or might be long, and then ended, and whose ending we cannot know because the news has not arrived yet. The deaths of those biospheres are in transit. The light we will eventually receive and interpret as evidence of living worlds may in some cases be the light from worlds that have been dark for millions of years. We will receive it. We will not know it when we do. Everything we have discussed tonight leads to one place, one conclusion that changes the way the night sky feels when you look at it. With the full weight of what the science actually tells us, the universe is in the business of making worlds. Some of those worlds reach conditions compatible with life. Some of those worlds, we believe, based on the evidence, produce life during the window when conditions are right. That life persists for some duration that varies enormously depending on the specific circumstances of each world, the stability of the host star, the geological history of the planet, the specific chemistry that life develops, the timing of any catastrophic events relative to the evolutionary history. Some windows are brief, some may be very long, most close eventually, because the conditions that created them are not permanent. The habitable zone moves. The magnetic field weakens or collapses. The atmosphere evolves in directions that are not favorable. The star brightens past the threshold. The core cools. The feedback runs away. Something ends the window. When the window closes, the world does not disappear. The star continues shining on it. The planet continues orbiting. The rocks continue existing, accumulating new layers of geological history, possibly preserving in chemical or mineralogical form some record of what once happened there. But the life, if there was life, is gone. The conditions are gone. The window is closed, and the light from that world is still traveling outward in all directions. The photons that left it during the period when the window was open are still moving through space at 300,000 kilometers per second in every direction, carrying in their wavelengths and intensities and spectral signatures a record of what the atmosphere of that world contained when they departed. Somewhere out there, some of that light is heading toward Earth. Some of it will arrive in our lifetimes. Some will arrive after we are gone. Some arrived before we had instruments to interpret it. When it arrives, we will measure it. We will analyze the spectrum. We will find chemical signatures consistent with biology. We will write papers. We will put that world on the candidate list. We will not know that the window closed. We will not know how long ago. We will know only what the light says, and the light is old, and the world it came from may have changed in ways we cannot detect. The universe may not be empty. The universe may be full, genuinely, historically full, of former windows, of places where the lights came on, and something used them, and then they went out again, of libraries that were written in and are now silent, of porch lights that are still on, technically, because the sun still shines on those worlds, but where the houses they illuminate have been dark for longer than our species has existed. We are inside one of the windows that is still open. That is the actual situation. Not a metaphor, not an analogy, the actual physical, chemical, astronomical, geological situation. Earth is a world currently inside its habitable window. The window has been open for approximately 4 billion years. The window will remain open for approximately 1 to 1.5 billion more. We are past the midpoint. The evening is here, the day is done, and the night is coming, but the evening is warm, and the evening is several 100 million years long, and we are in it right now. This knowledge is recent. The specific numbers, the habitable zone calculations, the stellar evolution models, the geochemical evidence from Mars and Venus, the exoplanet catalog with its 6,000 confirmed worlds, the paleomagnetic analysis of Martian meteorites, the deuterium ratios in the Venusian atmosphere, all of this has been assembled over the past century, with most of the specific insights coming in the past few decades. The species has had this knowledge for an extremely small fraction of its total existence. Most people alive today do not have it in any detail. The implication of it has not yet fully filtered into the culture. You have it now, or at least the broad shape of it. When you walk outside tonight and look at the sky, you will see it differently than you did before. Not as a void, not as a crowded neighborhood, as an archive, as a record of times, some of which overlap with ours, most of which don't, as a collection of letters, all arriving now, sent from different times and different places by senders whose current status you cannot determine, as a set of windows, most of which are already closed, some of which may still be open, and one of which, the one you are standing on the inside of, is definitely open right now. Tonight, the oceans are liquid, the air is breathable, the magnetic field is up, the carbon cycle is running, the seasons are turning. The geological clock that has been operating for 4 billion years is still operating. The thing the planets only get to do for a bounded fraction of their existence, the thing called sustaining life, is something this planet is currently doing. You are an instance of that. Whatever else is true, that is true. Right now, tonight, the porch light is on, the house is warm, the night is large and old and full of letters from former evenings, some recent, most ancient, arriving continuously at the speed of light. You are inside one of the evenings that is still happening. You will not be inside it forever. Neither will anyone else who is currently alive. Neither will any civilization that currently exists. Neither will the planet itself, given enough time. But the window is open now. That is everything. That is the only thing that matters tonight. The window is open now. Somewhere out there, there may be another world with its window still open too. A world whose light will arrive here eventually, carrying chemical fingerprints of biology in an atmosphere over a liquid ocean under a functioning sky. When that light arrives, we may not yet have the instruments to read it properly. We may not recognize what we are seeing. We may file it in a catalog and move on to the next target. Or we may finally have the instruments and the understanding and the willingness to sit with the full weight of what the data is saying. Either way, the letter is in the mail. The mailbox is enormous. The delivery continues whether anyone is watching or not. The lights are on here. Sleep well.